So here, continuing from the last video, I will continue. I will again discuss the dimensional analysis some of the more quantity physical quantities. So let us start with the moment of inertia. So what is moment of inertia? So moment of inertia is defined as we mark it as 1. So moment of inertia is defined as inertia is nothing but the mass and moment is nothing but the distance square from a certain point. So it has a dimension of m into r square with obviously some constant terms multiplied. So m has a dimension of mass has a dimension of capital M, and r, which is distance, has a dimension of L. So it gives you L square. So moment of inertia has a dimension of ml square. So you see it is quite simple to calculate the dimensional formula of any quantity. So here let us take another example of permittivity. So how you calculate the permittivity? So permittivity is epsilon. Now how epsilon is calculated? So permittivity is basically related to the force as 1/4 pi epsilon q square divided by r square, which can be q1 q2 or like that qi qj for force fi fj and distance rij. So it can be vector obviously. So but here I am writing it in simplified form. Now using it, epsilon can be defined as 1/4 pi f q square divided by r square, which gives dimension of epsilon as, if you are using epsilon, which is a general term for permittivity in any media. So where an epsilon naught represents basically in the vacuum. So using that, the force has a dimension, as we know, ml t to the power minus 2, which is mass multiplied by the acceleration, and q is nothing but it, we have already discussed about, and it, and then r square is nothing but the length square. So permittivity will have a dimension of m inverse L to the power minus 3 and t cube into I. Let us check it again. So m inverse L square and L gives you L cube, which goes to minus L cube, and then t, which is here, and t to the power minus 2 adds to become t cube, and then I, which is the current. So here is the dimension of permittivity of media. Now let us go to some more quantity. Now let us calculate the dimensional formula of permeability. Now permeability is related to the magnetic field using the Biot-Savart's law. So it says that B equals to mu naught by 4 pi, or mu basically, if you are taking in some media. So general term is mu. So mu by 4 pi I and dl cross r divided by r cube, where r is a vector. If you use this formula, then let us calculate the dimensional formula of mu using relation b into 4 pi r cube divided by I dl cross r. Now, for pi is a constant, B is the one quantity whose dimensional formula we have already calculated, and R cube. So what is B? B is related to force divided by Q into V. So force is mLT to the power minus 2 divided by IT into LT to the power minus 1, using the Lorentz force law. And then R cube has a dimension as L cube, and the I is nothing but IT. I is nothing but I, and DL is again L, and R is again L. So if you see, by simplifying it, what you find as the dimensional formula as L cube is cancelling out here with L, so mu becomes M L T to the power minus 3 I to the power minus 2 as the dimensional formula of magnetic permeability. Just verify it. M L T to the power minus 2, and this power is added, which becomes T to the power minus 1 basically, and T is cancelling out, so it leaves with T to the power minus 2, and I becomes I square, which gives you I to the power minus 2. So the correct formula, or dimensional formula of permeability or magnetic permeability will be mLT to the power minus 2 I to the power minus 2. Now let us go to the another quantity, power. Now let us calculate the dimensional formula of power. So power is defined as work done per unit time, and it has a unit as watt. So power, if you are representing it by P, it is defined as W, which is work done, divided by T, which is time taken. So, what is the dimensional formula of work done? Work done is nothing but a form of energy. So it has a dimensional formula as ml square T to the power minus 2, which is force multiplied by the displacement, and then divided by the time, which is the dimensional formula as capital T. So the dimensional formula of power will be ml square T to the power minus 3, as simple. Now let us go to some other quantity, which is pressure. So pressure is simply defined as force per unit area. If you are representing force, pressure as a small p, then it is nothing but force per unit area. Now pressure is a tensor quantity, and so it has more than 3 components in 3 dimensions. So here, how the pressure is defined, force per unit area. Now, so what is the dimensional formula of force? ml T to the power minus 2, which is mass multiplied by the acceleration, divided by the area, which is L square. So the pressure, dimensional formula of pressure will be simply m L to the power minus 1 T to the power minus 2. Now let us calculate the dimensional formula of reluctance, which has a dimension as Henry inverse. Now Henry inverse is nothing but related to basically L inverse. Reluctance is 1 upon L, or 1 upon L, which is called inductance. So inductance, now as we recall, inductance has the dimensional formula as 1 upon E divided by di by dt. So what does it mean? It can be written as minus of di by dt divided by E, where E is the electromotive force. So it can be written as like this also, rather than small e. So now di by dt is your I as the current divided by the time, and this E is basically Q by, potential energy divided by the charge. So potential energy is ml square t to the power minus 2 divided by it. Now simplify it. So it will go R has a dimensional formula as I square T divided by M L square T to the power minus 1, which further simplifies to give you M to the power minus 1, L to the power minus 2, and T to the power 2 and I to the power 2. So this is your reluctance, which is just inverse of inductance, and it has the dimensional formula. You see how we can calculate it using the what we call self-induction formula, and we find that it is it depends on minus 1 to the power of mass, minus 2 of the length, and two powers of second powers of time and current. Please note it down. Now let us calculate the dimensional formula of latent heat. So latent heat is defined as L, which is divided by Q divided by M, where Q is the heat. Right? So it can be heat of fusion or heat of basically evaporation. Right? So here, so Q by M, it means L, where Q is this ml square T to the power minus 2 divided by M. So giving you a dimensional formula as L square T to the power minus 2. Now let us go to specific heat capacity. So specific heat capacity is defined as S, the small s, is divided by Q divided by M into delta T, where T is the temperature. So Q is nothing but your heat stored in the system, and M is the mass, and delta T is the temperature, which is represented by theta. So its dimension will be L square T to the power minus 2 and theta to the power minus 1. Now let us go to the stress. Stress is another physical quantity which has the same nature which pressure has, which it means that it is sigma is force per unit area. So it is force is ml t to the power minus 2 divided by L square, giving you m L to the power minus 1 t to the power minus 2 as the formula for stress. Now let us go to surface tension. So surface tension is defined as Newton per meter, right? So F dot S, so if you define it as Y, so it is force per meter or pressure multiplied by R, which is usually the surface tension we calculate for different P into R. So it is force per unit length. So force per unit length is ml square, ml t to the power minus 2 divided by L, giving you m t to the power minus 2 as simple dimensional formula of surface tension. Please note it down. So let us start with another physical quantity, spin. Now spin is what? Spin is nothing but a form of angular momentum. So what is the dimension of angular momentum? It is kilogram square per second, right? So angular momentum is momentum multiplied by r, or distance. So momentum is P equals to mv, and so it is angular momentum so it has a dimension of kg meter square per second, ml square t to the power minus 1. Now let us go to some more quantities like viscosity. So what is viscosity? If you recall it, so viscosity is defined as it has a relation F equals to 6 pi eta RB. So from that relation, you can simply calculate eta is F divided by 6 pi RB. Right? So it can be defined as ml t to the power minus 2, and 6 pi is a constant, and r is nothing but L, and v is L t to the power minus 1. So giving you the dimension as m L to the power minus 1 and t to the power minus 1. Right? So let us go to thermal conductivity. Now this is a simple dimensional formula for your viscosity. Now let us go to thermal conductivity. So thermal conductivity is nothing but the energy per unit time and per unit temperature. So it is defined as K. So energy per unit time is nothing but in watt and divided by the temperature, which is in theta. Right? So, or delta T you can say. So it gives you m L square t to the power minus 2 divided by per unit time as T and the per unit temperature as theta. So giving you the dimension as ml square T to the power minus 3 and theta to the power minus 1. Now let us calculate the thermal resistance. So thermal resistance, dimensional formula for thermal resistance. So it is just inverse of thermal conductivity. If you take it as R, so it is K, 1 upon K, so it will have simply the dimensional formula of m to the power minus 1, l to the power minus 2, t cube and theta to the power 1. So this is simple. Now let us go to the Young modulus and the another quantity. So Young's modulus. So Young's modulus is related to stress divided by strain. Now stress is nothing but force per unit area and strain is delta L by EL, so it is a unitless quantity for a simple simple case. So this gives you force per unit area has a dimension nothing but m L to the power minus 1 T to the power minus 2, whereas delta L by L is dimensionless quantity. So dimensional formula of Young's modulus is m L to the power minus 1 T to the power minus 2. Please note it down. Now let us calculate the dimensional formula of spring constant. So how is the spring constant defined? So if W is the energy, so or U is the energy rather than, it is half of kx square. Using this formula, we can calculate the k. So k is 2 times u divided by x square. So now u, 2 doesn't contribute anything in the dimension, but u has a dimension of m L square T to the power minus 2 and x square is L square, giving you a dimension of m L to the power minus 2 minus 1 m T to the power minus 2 as the dimension. Now let us go to another quantity, which is torque. Now torque has a dimension of Newton meter because it is R cross P. If tau is the torque, it is R cross P, R cross F. Right? So it implies, if you take in simple terms, so tau has a dimension of L multiplied by F, which is mL T to the power minus 2. So tau has a dimension of m L square T to the power minus 2. Now let us go to another quantity, which is magnetization. Now magnetization is defined, or it has a unit as ampere per meter. If you are taking it as a capital M, it is defined as, its unit is ampere per meter. So it is I divided by L. So it is I L inverse. Now let us take to another quantity, which is magnetic moment. So it is defined as, if it is Newton meter per unit time. So it has a dimensional formula HML square T to the power minus 2 divided by T, giving you ml square T to the power minus 3 as a dimensional formula, where Newton is ml T to the power minus 2 and m as the dimension is L. So these are some of the physical quantities whose dimension formula has been calculated here. There are some more quantities which we are going to calculate further. Please note it down.